Okay, so we've been talking about acceleration as a function of velocity, and before we talked about an object that was at some positive initial velocity, and then it started to slow down, and as it slowed down, the acceleration decreased, so it slowed down less and less over time. Now we're going to talk about an object starting from rest, and it has some initial acceleration, but that acceleration decreases as the object speeds up. So the main two examples you could have for that is like a problem where you dropped an object, so it's like a free fall problem, except air resistance is not ignored, so it's not free fall, and that acceleration decreases as the object falls. The other example could be like a car starting from rest, and you hit the gas pedal, has some initial acceleration, but as you start going faster and faster, the acceleration decreases and decreases. And for both those situations, you end up approaching some terminal velocity. So when we have that type of equation, we're going to have an A equals A naught minus kV. So when we start from rest, we start with the initial acceleration, A naught, and then as our velocity gets larger and larger, our acceleration gets smaller and smaller until eventually our acceleration reaches zero, and our V is that terminal velocity. So if we wanted to actually solve for that terminal velocity, it'd be 0 equals A naught minus K Vt for terminal velocity. And so K times the terminal velocity would equal A naught. And so the terminal velocity would actually end up being A naught divided by K. And so we're not going to end up going any faster than that. But just like before, we can take this equation and we can turn it into a differential equation and solve for velocity as a function of time. So let's take a look at that. So I've rewritten the equation, but I've replaced A with dV over dt. And then the next thing we need to do is separate the variables. So I've separated the variables where we have dV over A naught minus kV equals dt, or another way to write that would be 1 over A naught minus kV dV equals dt. And just like before, we're going to integrate both sides. So I have the integral of 1 over A naught minus kV dV equals the integral of, we can think of that as 1 dt. So I've evaluated the integrals on both sides, and I get negative 1 over k times the natural log of A naught minus kv equals t plus c. And now I'm going to multiply through both sides by negative k. And now I'm going to do e to the power of each side. Next, I subtract A naught from each side. And then I multiply through divide both sides by negative k. So now I have V equals CE to the negative KT plus A naught over K. And then the last thing I have to do is solve for C, so we'll do that on the next slide. So for this problem we are starting from rest, so basically that means when t equals 0, V should equal 0 because that's going to be our initial velocity. So I'm going to plug in 0 for both values and solve for C. So when I plug in 0 for t and v equals 0, I get 0 equals ce to the 0 power plus a naught over k. Of course, anything to the 0 power is 1, so that's just 0 equals c plus a naught over k. And so we end up with c equals negative a naught over k. And so if we go back and plug in our value for c, we get v equals negative a naught over k e to the negative kt plus a naught over k, or the way I usually write it is v equals a naught over k minus a naught over k e to the negative kt, and if you really want the simplest version, then it's a naught over k times 1 minus e to the negative kt. Okay, so an example we have here is A equals 32 minus 0.1 V. This could actually be an object that's dropped from rest, except instead of using meters per second squared, we're using feet per second squared because the acceleration due to gravity is 32 feet per second squared. So what we see is that right when it starts, it's in free fall. But then as it gets moving faster and faster, the acceleration becomes less and less, approaching some terminal velocity. So we can rewrite this as a differential equation and then separate the variables. And then now that we've done that, we can integrate both sides, and that should not be a dt. That should be a dv right there. Alright, so integrate both sides. Now we multiply both sides by negative 0.1. And now that we have that, we'll do each side e to the power of each side. Alright, so now we have 32 minus 0.1v equals CE to the negative 0.1t. And then the next thing we'll do is subtract 32 from both sides, and then after that we'll divide both sides by negative 0.1. So now we get v equals CE to the negative 0.1t plus 320. And then our last step is to solve for c. And so remember we started from rest, so when t equals 0, v should equal 0. So we'll plug that in. And when we plug that in, we see that c has to equal negative 320. So we end up with v equals 320 minus 320 e to the negative 0.1 t. So we noticed there we said earlier that the initial velocity equals 0. So if you plug in 0 for t, you will get 0. Also, you should notice that as t approaches infinity, the velocity approaches 320. So for this particular object, the terminal velocity would be 320 feet per second. Now, from there, if we wanted to, we can find x, because remember x equals the integral of v dt. And we're not going to go through that solution here, but it's definitely something you can do. You can also find a, because remember a equals the derivative of velocity with respect to time. So by taking this equation we have right here and finding the integral, we can get position as a function of time. And by taking that equation and taking the derivative, we can get acceleration as a function of time. Alright, and that's all you need to know about acceleration as a function of velocity, and using that to figure out velocity, position, and acceleration as a function of time.